Hey, got it. Okay, good afternoon, everybody. Today we are very honored to have Dr. Caisheng Wang from Wayne State University to give us a talk on power management and load transient mitigation of fuel cell systems. Dr. Wang and I know each other for many years. When I was in Michigan, we had a lot of pleasant collaborations mostly on the electric vehicle development. Dr. Caisheng Wang received the bachelor and master degree from Chongqing University, China in 1994 and 1997, respectively, and the PhD degree from Montana State University in 2006, all in the EE. From 1997 to 2002, he worked as a research engineer and later the vice chair of the Department of High Voltage Engineering at the Zhejiang Electric Power Research Institute, Hangzhou, China. In August 2006, he joined Wayne State University, located in Detroit, Michigan, where he right now is a professor with the ECE department. Dr. Wang has been very widely funded with a totally $10 million, meaning he's very rich now. He has been teaching and conducting research in the area of renewable alternative energy systems, power electronics, distributed generation, microgrid and smart grid, and electric vehicles. He has a lot of journal and conference paper published with very high citations. Several book chapters and 2 books. He has been serving as associate editor of several international journals, including IEEE Transactions on Smart Grid, Electric Power Component and Systems, SAE journals of electronic and electrical system for passenger cars, and served as a grant review panelist for NSF and the Department of Energy. He has won awards include Excellence in Teaching of College of Engineering, Excellence in Teaching of Division of Engineering Technology at Wayne State, IEEE EDPG Prize Paper Award, and MSU Foundation Graduate Achievement Nomination Award, and Honorary Citizenship City of Bozeman, Montana Award. With that, I will leave the floor to Dr. Wang. Now it's yours.
First of all, thank you very much for Professor Bae's kind introduction there. For those awards that I like most is the honorary citizen of Bozeman. I stayed in that small town for about 4 years for my PhD study. So can I share my screen?
Yes, you can go ahead, I believe.
Okay. Okay. And also many thanks to Professor Chen for also giving this opportunity. So yeah, I would like to and thank you all for coming to this talk. I'm going to talk about some of the work I have been doing on power management and load transient mitigation of fuel cell systems. I hope it's not going to be too boring. But what I'll try to finish in as suggested by Professor Bae and Professor Chen, I'll try to finish it in 45 minutes. But if you have questions, feel free to ask, okay? So the first thing I want to say here is give a very brief introduction about Wayne State. Although Professor Bae already said that Wayne State is located in Detroit, Michigan. I don't know whether you have heard about Wayne State and where which city is located in. Actually, it's located in Detroit. It's in the midtown of Detroit. So this year, Wayne State is about 150, almost 155 years anniversary. So it's founded in 1860. And the Wayne State has about 25,000 students. When I joined Wayne State, it was about 30,000. It has been dropped quite a bit since then. But We have various programs, degree programs, certificate programs, and we have 13 schools and colleges, of course, including College of Engineering, School of Medicine, and various other colleges there. The annual research expenditures is about it's about $250 million. So with that, I'll start my my seminar here. So after a brief introduction on how fuel cell works, the different fuel cell systems there, I'll talk about the control of fuel cell systems, and after that, I'll talk about power management of a hybrid energy system consisting of some alternative sources as well as the fuel cell system there. And particularly, I'll talk about the low transient mitigation for fuel cells system there, because the low transient can be an issue for fuel systems. And after that, we'll talk about the power converter ripple current reduction, because fuel cells is a DC system. We may need to have a power converter for that. So the current ripple could also cause negative impact on the fuel cell there. So we need to do something to eliminate those current ripples. Okay. So this slide shows how a fuel cell works. The fuel cell is a stationary device. It's convert the energy in the fuel, the chemical energy, into electrical energy directly through electrochemical reaction. Okay, so as you can see here, this is more or less for a hydrogen-based fuel cell. Okay, like a proton exchange membrane fuel cell. We're going to talk about a little bit more about that. So like at anode, we have hydrogen. It loses electrons, so electrons will go through the external circuit, and the hydrogen protons go through the electrolyte. Normally it's a membrane, and then are going to combine with the oxygen and the electrons to form water. The water can be either in a vapor, in a gas form, or in a liquid, depending on what's the temperature of the fuel cell there. So as you can see from this slide here, I promise we're not going to see, this will be probably the equation we're going to see for the whole, the same line here. If you look at, the voltage of a fuel cell, a single cell here, under the standard condition, like the 1 atm and 25 Celsius degree, what we get is only like a little bit less than 1.2 volts. So in order to get a high voltage and high current, like the photovoltaic panels, we have to put quite many cells together to form a module, then like array and a stack, as you see here. So this is a structure of a fuel cell stack here. It's kind of has a modular design here, so you can see this kind of like a membrane electrode assembly. So some fuel cells have this MEA. We can do like a hot swap, so we can put in and out even the fuel cell is operating there. So we need to put quite a few cells in series to give us enough voltage there, and we need to put them in parallel to give us enough current. Okay, then we can have a workable fuel cell system there. Okay, so there are different types of fuel cells. Depending on the operating temperatures, we can have low temperature fuel cells and high temperature fuel cells. For low temperature fuel cells, basically, it's good for like transportation applications, like fuel cell vehicles, right? For fuel cell vehicles, mostly now if not all, the using, the PEM fuel cells. We call polymer electrolyte membrane fuel cells, or sometimes we call proton exchange membrane fuel cells. But we can have like alkaline fuel cells. They have been used for the outspace applications. Have the phosphoric fuel cells and direct methanol fuel cells as well. And for high temperatures, we have solid oxide fuel cells, which is very good for like distributed generation applications, for the stationary applications, and molten carbonide fuel cells and other type of fuel cells here. Probably will not be able to touch all of them, but I do prepare some tables here to compare different fuel cells. I don't want to overload you with this kind of detailed information here, but I want to point out is for you to pay attention to PEM fuel cell and solid oxide fuel cells, because for PEM fuel cell is basically all of the majority of the fuel cell vehicles are using PEM fuel cells. For solid oxide, that's very good, very promising for the stationary power generation applications. And we're going to look at those two fuel cells in particular. Okay, so let's look at the PEM fuel cell. And the operating principle I just pretty much already talked in the previous slide there. And it can be pretty efficient. Okay, it can be like 40 to 60% depending on what kind of operation we look at. If we have a combined heat and power, it can be more efficient. If we just look at the electrical part, and then it may be just around 50% there. Okay. By the way, let me check with you guys. Do you know how efficient a typical internal combustion engine might be? For example, a gas engine might be.
25-ish%, I believe.
I think, yeah, roughly right. It's around 30%. Okay. So compare with the internal combustion engine, it is more efficient and it is clean, right? So if you run on the hydrogen, the resultant we got is just water. Okay, so that's very environmentally friendly. Okay, and here the picture shows a 1 kilowatt unit from Ballard. Ballard is a leading company in manufacturing PEM fuel cells. Okay, if you are interested, you can go to this website to get more information here. Okay, and this slide shows a schematic diagram of a solid oxide fuel cell, SOFC. So SOFC, compared with PEM fuel cell, it is a high temperature fuel cell. Okay, so it needs to run at over like 600 Celsius degree. There are some medium temperature solid oxide fuel cells, because this is a dynamic research area. So people are proposing new materials. So we have a different type of SOFCs. But compared with a PEM fuel cell, the operating principle is a little bit different. So for PEM fuel cell, we have the hydrogen protons, right, moving across the electrolyte and reach the cathode side. For solid oxide, it's actually oxygen ions pass through the electrolyte and reach the anode surface and then produce water. Okay, so you see the water is actually for PEM fuel cell, it's happening on the cathode side, channel side, and for the solid oxide, it's different. It's on the other side. Okay, and there's normally there are two different structures for solid oxide. We can have the tubular structure. Tubular structure normally it's just, I would say it's more reliable. Okay, but it occupies a bigger volume. Okay, we can also have a planar structure, which is more compact. Okay, you can see this kind of like the MEA we talked about before, the membrane electrolyte or electrode, we may call it assembly. So for the planar SOC, we can have a smaller volume, but it's more challenging in like manufacturing because we have this kind of because it's high temperature, right? How to get seal together. The different materials may have the different like a temperature expansion coefficient. So how to seal them together? That's not an easy job. Okay, but people working on it, they have making pretty good progress on it. Okay, fuel cells can be used in a variety of applications. Okay, um, residential, automobile, even for heavy duty vehicles, and for like a building, it can provide not only electricity but also heat, because you see the fuel cell, when they do that kind of electrochemical reaction, they also produce heat. So it's the combined cycle. We said we have the combined heat and power can make the overall system even more efficient. Okay. In different countries have their research and development programs targeting for fuel cell development, and you probably guys have heard about the hydrogen economy, right? So basically, the hydrogen economy is taking the hydrogen as the the energy carrier. Okay. Like here in the US, in the European Union, they have their roadmap. China, Korea, Japan, they all have their like a hydrogen economy roadmaps. So on the right, you see it is our hydrogen economy roadmap. You can see it's a pretty like aggressive goal there. And if you look at this the spider web map here chart, if you look at those parameters or objectives there, look at the peak energy efficiency, the power density, specific power, cost, and how fast can start, and durability. And the fuel cell actually are making a quite good, like impressive, achievements in the past like decade. But there are only two things I would say. We still need to see some big improvement. There is cost and also the durability. Okay, that two things there. If we can really make some breakthrough, then I will see a bigger, a faster adoption of fuel cell systems. Okay, now let's look at for those applications. Let's particularly look at the transportation fuel cell systems and the stationary power generation. Let's first look at the transportation, like electrical vehicles, like fuel cell vehicles. So we need, of course, we have this fuel cell stack there, right? Then we need to have various, units here to make the system work for the transportation application there. We need to control, for example, the fuels and also the airflow control, the oxidant, right? We need to control the temperature, right? Of course, because it produces heat, we need to keep the temperature for the fuel cell at the right temperature, not too high, not too low. And also need to do the humidity control. That's also important for the PEM fuel cells. The membrane there need to be humid, need to be wet, but cannot be too wet. Too wet, then we're going to see flooding there. That's not good. And that may cause some accident. If it's too dry, we may see fraction of the membrane and that may damage the fuel cell. Okay. And when we get the output, the electricity, the DC there from the fuel cell, and then we need the power electronic converter there, right? We may need to go with some other units like the battery or capacitor, and then provide the proportion, the traction power to drive the motor, and then to propel the vehicle. Okay. Well, there are quite some commercial fuel cell vehicle in the market now. Particularly, I would say it's a Toyota Mirai. which is now is commercially available. I don't know how much it's going to be. You guys can go to its website, but I'm not say I advocate any specific like the fuel cell vehicle here. It's just it's interesting development. You know, if you're interested, you can go there, but I believe it's not cheap. So as we discussed before, the cost reduction is one of the major factors, you know, for fuel cell, you know, development. Okay. And for the stationary applications, you guys probably heard about like microgrid, right? Distributed generation there. So fuel cells can be a very good one. You know, for example, you can use fuel cell system as a backup unit, right? My labor, they have a diesel based, you know, backup units there. It's pretty loud and it can generate those pollutants there. But for fuel cell, it can be very quiet, you know, and it's clean. Okay. For stationary system here, you know, for those control there can be very similar to the transportation application there. For example, fuel cell vehicles. But you know, the output can be different, right? It can be grid tied, you know, or it can be standalone. For standalone, there probably we also need some kind of energy storage system to work with it, but it just is optional. Okay, and for stationary, as we discussed before, we could use different type of fuel cells. Maybe we use the high temperature fuel cell there to have a CHP, combined heat and power systems, right? For high temperature fuel cells, it's not so good for, you know, the regular fuel cell vehicles, particularly for the passenger vehicle, because at the high temperature you have to wet, you know, the fuel cell unit to get to the right temperature, right? But for stationary, you know, that's not a problem. You know, so we can use, you know, high temperature fuel cells there. Okay. As some example here, you know, Siemens have this kind of 100 kilowatt SOFC, the combined heat and power systems. It can produce electricity and hot water at the same time. Okay, and there's another like a 250 kilowatt. It's a good, you know, candidate for those microgrid applications. Okay, so this is just a summary of a control fuel cell system there. We need to have those fuel control, air oxygen control there, humidity control, temperature control, the thermal management and power management. If we have, you know, for either, transportation applications or stationary applications, we need that, you know. But of course, for the output of the fuel cell system, it depends on the applications. We can have a different way to do the power management. Okay, so now let's look at a example system, a hybrid, you know, energy system here, consisting of wind, and solar, and battery, and also fuel cells here. Okay, so this system here certainly is not for fuel cell vehicles. It's for stationary applications here, right? Because we have wind and solar. But the system can be standalone, or we can have a grid tie system here. So, you know, the power management of this system is kind of straightforward, particularly at a high level here. So if we have the resource, you know, the resource here basically is from wind and solar. The fuel cell and electrolyzer here, together with the batteries, it's like act as an energy storage. Okay, so if we have enough wind and solar power, right? You know, to support the customer load there, and also the self-consumption load of the system here, then the extra amount of power can be used to we can turn on the electrolyzer, and to generate, use the additional excessive power to produce hydrogen. And that amount of hydrogen can store in the hydrogen tank there, okay? But when there's not enough, for example, in the evening, we don't have any solar power. So we can turn on the fuel cell by using the hydrogen stored there and supply the electricity back, together with maybe the wind energy system or the battery there to support the electricity to the customer, okay? And we do have a hybrid energy system developed on Wang State campus, okay? And this is a picture for that system there. Dr. Bay, I don't know, when you visit Wang State, I don't know whether I get a chance to show you the system of this hybrid system here, but it is a hybrid energy system consisting of wind and solar. You can see the wind turbine. It's a vertical turbine, and we also have solar there, solar array. So total is about 10 kilowatt here. We did have a fuel cell for this as well, but the fuel cell system is not working now. It was a PEM fuel cell unit. So you can see the durability of fuel cell. That's another, factor. Those fuel cell manufacturing and fuel cell research should be really focused on. The other system, for example, the wind and solar are still working just fine, but the fuel cell is not working anymore. Okay. And now let's switch our gear to no transient and no transient mitigation here. So because in the real world, we do see a lot of transients, okay? For example, in the residential applications, right? This is the data recorded by a smart meter, okay? You can see, for a single home, the power level can be really, volatile. And if we look at the specific type of load, like we look at, the computer monitor, we look at, the vacuum cleaner, we look at, even the lighting bulb, we can have those transients. If you turn it on, then normally there will be some kind of inrush current, right? So those things can be bad, can cause problem. And in the car, all automobile loads, they also have a different type of transient there. So you have like inductive, capacitive, right? And particularly for electric vehicles, right? We have a motor. If you just turn on a motor, they're definitely going to see a big inrush current that can be 5 to 10 times bigger than the steady state value. So if you do not treat it well, that can cause problem. It can trick your protection system to mistakenly make the system think it's a fault, right? For fuel cells, that particularly, it can cause negative impacts. We're going to talk about that in more detail in the following slides. Okay, so let's see, we have a different type of load transients there. So how to characterize and model this? Forget about the equation here. Okay, you just look at the figure here. So we can model that, depends on how big the transient is, how fast the transient is. Okay, we can use some generic model there to characterize those transients. Okay, but in case you are interested, you can always go to the paper here. That's one of my papers. You can go there to get more details. But here comes the fuel cells, right? We said, there are always different kinds of load transients. But why we need to have this kind of load transient mitigation control for fuel cells? Because fuel cells, they don't like those transients. Okay, those load transients can cause negative impacts on its durability. Because suddenly the load jump out, right? We can see an excessive, consumption there. That can cause very low reactant condition there. That can be harmful. or suddenly drops down there, right? So those things, because in general, fuel cells are not fast response unit. Their response is relatively slow. So, the transients can cause negative impacts on fuel cells durability, okay, and reliability. So we want to mitigate those, okay? So how to do that? Normally, okay, we can form a hybrid system together with some other like fast dynamic sources here. For example, we can form a fuel cell, a battery system. We can form a fuel cell, like ultra capacitor system there, right? We can form those systems together and let the fuel cell just take care, let the fuel cell take care of just the steady state power. Okay, so in that case, fuel cell can be better treated and not cause much of trouble there. Okay, how to exactly do it? Say let fuel cell just provide a steady state, that other fast dynamic sources take care of the fast transients here. So the very typical way we can go is say we can go with a low pass filter, right? We can use a low pass filter. Use that one to control the fuel cell and let the fast dynamic sources take care the fast transit. And we can also go some more complicated methods, like we can go with the system identification to identify the steady state, part of a transient. Okay, so then we use that one to control the fuel cell. Okay, there are some other methods we can use, like neural network based approaches and other machine learning based approach as well. We can identify where the transient might be, look at the different transients. Okay. So, okay, for example here, we have a fuel cell system, right? It's providing something to the load, but it's interfaced through what? This is a boost DC converter, right? If you have taken some courses on power electronics, that's just a boost DC converter there. So we can control by measuring, of course, say we can measure the current there and go through a different approach there. We can go with like low pass filtering and then get this get just the slow response or steady state there and use that one to control this DC converter. So the fuel cell, we're going to take care of the slow dynamic part. Okay, but of course we could use some other way to do it. Use like machine learning approach, for example, there, which will be similar. Okay, so some result here I want to share with you. So say we have some transients, low transients, right? Through that kind of, for example, the low pass filter, we can let the battery will take care of those fast transients there. The fuel cell will only take care of this, the very smooth response here. So this is fuel cell likes it. That's good, and not only the low transients, as you probably just saw the fuel cell and the boost DC converter, right? So a fuel cell stack normally going to work together with some type of power converter. Okay, the power converter, the input to that power converter actually is what? Actually is the output of the fuel cell, right? So let's take, say if you want to convert fuel cell is DC, right? Fuel is DC, you want to get AC. You put an inverter here. We have to have an inverter here, right? So this inverter and and the curve you see here below here, that is like the typical input, DC current for a inverter. So it's not smooth. It's very, like a poor setting, right? So, fuel cells don't, as I said, fuel cells don't like to have this kind of thing, right? So how to like reduce the ripples, even for the DC-DC converter, we could have some like ripple there, say, we could have some ripple there. That ripple, we want to reduce it or eliminate it as much as we can, okay? So the question now will be how to reduce those ripples. There are different ways to do it. A different way to do it, a typical way to do it is we can have the interleave DC-DC converter, okay? In each phase, we could have a bigger variation there, but because in the interleave, there's like phase shift. I have a slide for that. So if we combine together the overall current, okay, so overall current here, IFC, can be can have a much smoother current there with a much reduced, the current ripple. Okay, so for example, this one basically show the project we have been working on. We just finished the development of a 180, kilowatt, DC-DC converter. Okay. Okay, so the ripple, there's a requirement, there's a design requirement for that DC-DC converter, which means this, like the output current from that fuel cell will see a very small ripple there. Okay. So one more slide to show that some detail here. So like, for example, in this slide, you see just like a two-phase. These two phases are interleaved together. And, if we just look at one single phase there, we can have, like a bigger variation, right? If we have like a two phase, we put them like an interleave together. For two phase, there are 180 like out of phase there. And then the overall is the, like the combination, the superposition of these two will add together, right? So then the overall current will have a reduced ripple, okay? You don't want to add them together directly. If you add them together, you're going to get an even bigger ripple, right? So if you offset by 180 degrees here for the two phase here, you can get a reduced, a ripple, okay? That's basically the idea for the interleave operation, okay? And we could further reduce the ripple there, even for each phase. We can use like a couple inductor, okay? Now for couple inductor, the overall current ripple may be the same if we keep, the overall leakage inductance the same, but the waveform, the variation for each phase of that couple inductor can be further reduced, okay? Just another example here, you see, for that A phase, I talk about, the 180 kilowatt the converter we develop. Okay, we have A phase, interleave there. Okay, you can see that the top figure shows, the A phase current there. Okay, you can see there are 45 degree between two phases there, okay, and they are interleaved together. And you see the overall current. This is the overall current. The current ripple now is what? It's much reduced. It's less than 1%. Less than 1%. Okay. So this is a picture of the converter we developed. Okay, it's we use a silicon carbide, switching devices and silicon carbide diodes for the converter, and we tested the converter for about 40 minutes at the ready power there. So efficiency was 99.1%. And the power density, including everything here, like the enclosure and the cooling plate, everything put together, there is greater than 15 kilowatt per liter. We're pretty happy with the performance of this. So for this one, the input ripple there is being kept like around less than 10 amp. Okay, less than 10 amp. Okay. That's about it. I want to introduce, what we discuss there from the introduction of the fuel cell system there to the control needs of the fuel cell systems to the power management of a hybrid fuel cell system there, as well as the load transit mitigation. I just talked about. Okay, so the conclusion here is the fuel cell system is a relatively complicated system. So we do need to have a careful control and power management for such system. Okay, need to have the fuel control, the airflow control, right? The pressure control, the temperature, the thermal management, and also the humidity control. And when we get the electricity, how to do the control on the electrical part. The converter control there, right? If it's grid tied, we need to do the grid tied control. If it's for electric vehicle, then we need to do motor control. So all those kind of things, okay? And particularly there can be a different type of load transients, right? For both stationary and transit and transportation fuel cell system there. We need to have the measures there to mitigate, to reduce those load transit, to improve the overall system reliability and durability, because fuel cell system don't like to have those transients, because that can cause negative impacts on its operation and lifetime. Okay, and I talk about the example, like give the 180 kilowatt DC-DC converter we developed at the Wang State as example to show how we can, when we design a converter, how what kind of thing we can consider for reducing those current ripples. Okay, and that's about it. And before let's go to the Q&A session there. I want to introduce this REU opportunities at Wang State. It's an NSF research experience for undergraduate students there. The theme is for sustainable manufacturing. Okay, if you are undergraduate students, if you are looking for summer opportunities there, please consider this one. I think it's a good opportunity. Okay, please go to the website here to get more information there. And I think it will be, the stipend will be 6,000 for the summer, and it will the lodge will also be covered, room and board will also be covered there. I think it's a pretty good opportunity. And I am one of the faculty mentors there. There are a group of faculty. You can go to the website and look for the potential topics there. You may find something interesting to you. For me, I believe it's related to some power electronic converter development. All right. I believe that's all. I'll be happy to answer any question you might have. Thank you.
Thank you, Dr. Wang. Now it's time for the questions from the students.
So I have a question. I was really interested to hear about the hybrid wind PV and fuel system. And I was wondering if there's been any research into using that in commercial buildings that use a lot of energy, or implementing that as kind of a resilience aspect for community shelters during hurricanes and winter storms?
Yes, Liz, thank you for the question. I think, yeah, there's quite some research efforts on that, and I believe if you search, you should be able to find quite some papers there. And well, I can share my paper with you. It is on that. Let me go back to there. It's this paper. It's a hybrid system there. I know some people are proposing to using this kind of alternative or renewable sources, right? Hybrid energy system there from different sources there, depending on whatever the source might be available. For example, in the evening, we probably don't have solar, but we have some other energy sources that can have a more reliable, the output there. If you want, in addition to this paper, you may, it's a review paper. Okay, it's called a review on a hybrid. If you Google my name, or if you go to my Google Scholar, you should be able to see that paper there as well. It's a review paper. It's a task force of for IEEE task force here. It's I think in that paper talk about, well, that paper has been published quite a few years ago. But you're getting the sense there. There are also some example system was given. So at different locations worldwide, they have some small or maybe to the megawatt level hybrid energy system there.
Thank you. I'll definitely look into that paper.
Okay, sure.
Hi, Dr. Wang. I had a question about the slide where you were talking about decreasing ripple with power electronics with fuel cells. Were you saying that the fuel cell itself operates at a slower condition than a power electronic converter, so interleaving it decreases the ripple? And if so, how would interleaving it decrease the ripple? Because wouldn't that make the power electronics operate faster?
I'm
sorry. I was trying to understand, but I was a bit confused.
Let me go to there. So for here, well, let me try to repeat your problem. I don't know. I fully understand your question here. You said, fuel cell, yes, itself is relatively slow in response because of its electrochemical device. It'll convert, the energy in the fuel and into electrical energy, right? And there's a process there. The fuel and the oxygen has to diffuse to the right actual reaction site, so that the reaction can happen, so that can produce electricity and also heat. So it itself, like it likes to see, if possible, they would like to stay at a constant load. But of course, that's not the case, right? For the actual application, we're also going to see the change there. So, but say if there's a change, the fuel cell want to see something happen slower. Okay, so our job will be, we're going to design a converter, okay, or together with some other fast dynamic devices, so that, for the actual load demand, so whatever that transient might be, okay, for the fuel cell, they're still going to just take care of the smooth and the slower the dynamics. Okay.
Oh, so providing more conditions to meet that slow transition.
Right. We'll have to do the control on the converter, on the other fast dynamic sources part, so that like the fuel cell will be better taken care of.
Okay, gotcha.
Okay.
Now I'm understanding. Thank you.
Okay, sure.
Hi, Dr. Wang. So the fuel cell battery looks perfect, right? We can extract hydrogen from the seawater and the emission is just the pure water. Do you think for EV application, the fuel cell will replace the lithium battery? We just replace our gas station with hydrogen station, go there, recharge, only takes a few minutes. But
that's a very good question. You know, fuel cell, it is, if you look at, let me go back to the slide here. Let me see here. If you look at, you know, what fuel cell does, the input is, for example, hydrogen, right? If you look at the whole cycle there, you know, it get water, and then say if we use the electrolyzer through some kind of electrolysis processor, we can split water into hydrogen, water, and oxygen again, right? So it's a complete sustainable cycle. Use your word there, it's perfect. A lot of people agree with you. The only problem here, as I said, is the cost and the durability. You know, right now it's still pretty expensive, and the durability is also an issue. So if the scientists, particularly from the material side, if they can do come up with some kind of revolutionary breakthrough, then I believe fuel cell definitely is very, very promising. That's why you see different countries, they all have this kind of like a hydrogen economy roadmap. You know, it's one option. So even say after the back in 2009, yeah, around that time, you know, when Dr. Stephen Chu was the Secretary of the Department of Energy, at the time, you know, the Department of Energy just cut off the support on R&D for fuel cells, because they said they believe at that time the fuel cell is still too expensive for fuel cell vehicle applications. But then around that time, we host a visit of a lead scientist from Argonne, I believe, national lab. I asked, him a question, say, how do you think about the future of the fuel cell? So because the DOE dropped the support for the fuel cell research program significantly at that time. So what's the future of the fuel cell? He said it's fuel cell, if you look at it, it's just too good to really stop doing the research. He believed there will be still a good future on the fuel cell. Now fuel cells kind of come back, okay, and in many countries. So I would say if we can address the cost and the durability issues, you know, we're going to see a brighter future for fuel cells.
Okay, thank you.
I have a question.
Okay, sure.
So you're talking about how SOFC cells could be used for combined heat and power. Is it possible to sort of feed in hydrogen on the fly with those and basically make a sort of a makeshift power plant, for lack of a better word?
You feed the hydrogen to what? To the fuel cell or to the?
Like feed in hydrogen on the fly. Like basically you have the whole cell running and then say you're running low on hydrogen. Can you keep it running and then put in more hydrogen?
Excuse me. Yeah, of course, in general, no matter it's electricity or the heat, right? All those energy will come from fuel.
Yep.
Okay, will come from fuel. So because the heat is just like a byproduct.
Yes.
For example, the solid oxide fuel cell, it has to be operated at a high temperature.
Yep.
So for those like in the residual fuel or the exhaust like the reaction like the water or vapor there, right? That can be better utilized.
Yes.
To form a combined heat and power system. So certainly if you want to get more there, sometimes you may put a little bit more to produce, because all energy still comes from fuel.
Yes.
Okay. Yeah.
Well,
sometimes even say if you just get electricity, right, and the heat maybe just wasted, so then the efficiency may drop compared if you use both heat and electricity.
Yes. I guess let me rephrase that. let's say the fuel cell is running and it's starting to run low on the solid oxide cells use hydrogen as the fuel, correct?
Well, for solid oxide fuel cell, it is it can handle it's we can have more flexibility in the fuel there. Okay. So sometimes you can just fill with like a CH4 directly. They may have for that fuel cell unit, they may have like an internal reformer. Okay, they can do that, convert the CH4 into hydrogen, or some fuel cell can use CH4 direct natural gas directly. And even for there's a mono carbon oxide, CO, that's really bad for PEM fuel cells. We have to really have like a pure hydrogen goes to PEM fuel cell, but for high temperature fuel cells like solid oxide, it does not matter. The CO we can use CO as well. CO will be part of the fuel.
Okay, thank you.
Okay, sure.
Okay, I think it's close to 2 o'clock, so probably we will just end here. And let's give Dr. Wang another round of hand.
Thank you, thank you.
Thank you.
Yeah, please do not forget about the REU if you are interested.
Dr. Wang, you can send the advertisement to me. I can send it to all EECS students.
Oh, wonderful. I'll send a PDF file to you.
Yeah, lots of students are looking for internship right now, so it might be a little bit late now. But I would be happy to send it to all EECS students.
Yes, yes. Appreciate it.
No problem. Thank you so much. I hope we keep in touch.
Okay,
you.
sure. Okay.
Thank
All right. Thank you. Bye-bye.
Bye.
Bye.